Patty Simpson with Simpson Math. In this video, we're going to learn about dispersion or spread of our data, how spread out our data is. We're going to learn about Chebychev's theorem, z-scores, and box plots or box and whisker plots, which are just a display to show that spread. Let's learn about Chebychev's theorem. Previously, we learned about standard deviation, and standard deviation we found was just the average distance that a data value is from the mean. So before we get deeply into Chebychev's, let's first show you a visualization of what we're talking about when we talk about that standard deviation with our data values. So here's an example. Suppose that in one small town, the mean household income is $34,200 with a standard deviation of $2,200. At least 75% of the salaries lie between what two values? We'll talk about that last sentence here in a minute, but let's just start with this mean of $34,200 and the standard deviation of $2,200. What's happening here? So if we look at a number line, and we talk about the salaries of the people in the town, we know that if they all were to share their salaries evenly, the mean average of their salaries is $34,200. I'm going to put that right in the middle, since that is, if everybody shared evenly, that's what everybody would get. Then that standard deviation is the average distance from the mean that a data value is. So I'm going to go up one standard deviation from the mean. I'm going to go up one of those distances, one 2,200 from that mean. And if I add 2,200 to that mean, then I'm sitting at 36,400. That salary, 36,400, is one standard deviation from the mean. And we said that, that's the average distance that a data value is from the mean. I'm going to go back one standard deviation from the mean. So again, I'm just going back that 2,200, that distance. And now I'm sitting at 32,000 exactly. That's one standard deviation below the mean. So, somebody's gone out into the town and collected salaries. And they found salaries that are all around here. But maybe that's not all the salaries. Maybe there were people that made more than that. So if I add another standard deviation to this, I'm sitting at 38,600. And there could be people that made that far out. And then in this area. And they could even go back. So maybe you had some people whose salaries were less than that. Maybe they're sitting at 29,000, just subtract 2,200, 800 from that. So this is two standard deviations above the mean, and this is two standard deviations below the mean. And remember, that distance, that standard deviation, is just the average distance that a data value is from its mean. Okay, so with this kind of in mind, let me go back to Chebychev's theorem. So Chebychev's theorem says that for any number greater than 1, so we're going to go more than one standard deviation out. For any number greater than 1, at least 1 minus 1 over k squared of the data values lie k standard deviations from the mean. What in the world does that mean? Let me help you out, okay? So we want our k to be more than 1. We're going to go more than one standard deviation out. So let's go out 2 standard deviations. So k is just representing the number of standard deviations that we're looking out. So in other words, here was 1 standard deviation out. This is 2. This is what we're making k right now, is out 2 standard deviations. And if I go out 2 standard deviations, I can plug that 2 into this little formula so that I have 1 minus 1 over 2 squared, which equals 1 over 1/4, or 1 minus 1/4, If I have one whole pizza and I eat 1/4 of it, that leaves me with, well, we can make a common denominator by writing this as fourths. You know, one whole pizza is the same as 4/4. Subtract 1/4, and I'm left with 3/4. Oops, 3/4 of my pizza. Or what this says is that 3/4 of the data lie within those 2 standard deviations from the mean. So in other words, we went out into the town and we collected salaries, lots of different salaries from the town. And we found the mean of those salaries, that's our mean. And we found out that the standard deviation, the average distance of our data were 2,200 away. We can now look at that and we know that 3/4 of our data, 3/4 of the salary, at least 3/4 of our salaries fall within between 29,800 and 38,600. So that's always going to be true no matter what the shape of our distribution looks like, whether it's right skewed or left skewed, or maybe it's this beautiful symmetric shape. It doesn't matter what our distribution looks like. At least 75% of your data is going to be within 2 standard deviations from the mean. Now, I can keep doing this, and we can do that again and say, well, what if k is 3? What if we go out 3 standard deviations from the mean? Then how much of my data will be there? I do this exact same thing where I say 1 minus 1/3 squared equals 1 minus 1/9. Well, again, I have a whole pizza and I just eat 1/9 of it. How much of it's left? Turn that 1 into 9/9. Do you agree that that's just equal to 1? Minus 1/9, which equals 8/9. So I know if I go out 1 more standard deviation, so if I add another 2,200 to this, so that I'm sitting at 40,800, and if I go back a standard deviation, so that I've gone out 3 standard deviations, that's 3 standard deviations above the mean. This is 3 standard deviations below the mean. I know that 8/9 of my data falls within that 27,600 and 40,800. So I know that 8/9 of those salaries are between that. So think about a business who wants to come into town, and they know the average salary of someone in town, and they know the standard deviation of that town, the salaries of that town. Then they can start to make decisions about moving a business into town or not. You know, if my business caters to people who make between 27,600 and 40,800, I know that 8/9 of the town has a salary between that. So it might be a good place for me to put a business. But if my business caters on the higher end of that, then all of a sudden I may not want to put my business in that town. So knowing the mean and how spread out your data is can really let you know something about that data set. We can keep doing this forever and ever, go out further and further, but really all we need to know for our class is that 3/4 of the data lies within, at least 3/4 of the data lies within 2 standard deviations, and at least 8/9 of the data lies within 3 standard deviations. Typically, when we talk about this, we're going to talk about it as a percent rather than as a fraction. So I say 3/4, but we know that that 3/4 is equal to 75%, because we want our bottom to be 100, multiply the top by, the bottom by 25, top by 25, so you end up with 25%. Or you can just simply divide, 3 divided by 4 gives you 0.75, which is 75%. This 8/9 is about 88.9%. So when we talk about going out 3 standard deviations, at least 88.9% of our data is going to fall within 3 standard deviations. So now that we know a little bit about Chebychev's theorem, which tells us no matter the shape, at least 75% of our data lies within 2 standard deviations from the mean, and at least 88.9% of our data lies within 3 standard deviations from the mean, then we can answer this question. At least 75% of the salaries lie between what 2 values? Well, we see that 75%, at least 75%, and we're going to think to ourselves, that's 2 standard deviations out. We know that at least 75% of our data is within 2 standard deviations from the mean. So I'm going to go out 2 standard deviations. This was 1 standard deviation. There's 2 standard deviations. And I'm going to go backwards 2 standard deviations. 1 standard deviation, 2 standard deviations. So I know between 29,800 and 38,600, between those 2 values lie at least 75% of the salaries. Some of them may be a little higher, some of them may be a little lower. Heck, all 100% of them could be in here. We just know that at least 75% of our data will be between those 2 values. If the question asks at least 88.9% of the salaries, then we would say it's between 27,600 and 40,800. So Chebychev's is really powerful, but because it tells us if we have our mean and we have our standard deviation, we can find out at least how much of our data falls within those standard deviations from the mean. Let's work some example problems where we use the Chebychev's theorem to help us solve the problem. First, let's remember what Chebychev's theorem tells us. Chebychev's theorem tells us that at least 75% of our data falls within 2 standard deviations from the mean, regardless of the shape of the distribution. The distribution can be right skewed, the distribution can be left skewed, the distribution can be some weird distribution, and at least 75% of our data is going to fall within 2 standard deviations from the mean. And at least 88.9% of the data is going to fall within 3 standard deviations from the mean. So let's use that information to help us solve this problem. The following data shows the marks obtained by a student in 2 subjects. At least 88.9% of the data lie within what 2 values? So here a student took a science test, and in that science test, the mean average of the test was 89 and the standard deviation was 15. And we want to know 88.9% of those students fell between what 2 grades? What was the range for 88.9, at least 88.9% of the students? Well, that 88.9% with Chebychev's tells me that we're going to go out 3 standard deviations. That at least 88.9% of our data falls within 3 standard deviations. So I always like to draw a number line to help me out. So I'm going to take that number line and I'm just going to add my standard deviations until I get out 3 standard deviations. So here's my number line. Right in the center of my number line is always my mean of my data. All of them shared their grades so that they all got the same grade. They all get an 89. And our standard deviation, we go up 15 points from that, and we're at 1 standard deviation. So add 15 to 89 and we get 104. Add 15 again, and we're now at 119. That's 2 standard deviations. Let's do the same thing backwards. So if we go backwards 1 standard deviation, then we're sitting at 74. So between 74 and 104 is out 1 standard deviation from the mean. But if we go out another standard deviation, go back 1 more standard deviation, and we're sitting at 59. So 74 minus 15 gives us 79. 59. We know that at least, Chebyshev tells us, at least 75% of the students scored between a 59 and a 119. That's what Chebychev's theorem tells us based upon that mean and that standard deviation. Now, I'm trying to find out 88.9% though, so I'm going to go out one more standard deviation. So add another 15, and I'm at 134. Go backwards another 15, so that we're sitting at, let's see, another 15 would be 44. So this is our mean of the data. Here we've gone out one standard deviation. Here we've gone out 2 standard deviations, and there's 3 standard deviations. Here we've gone backwards, so this one's below average, 1 standard deviation. That one's below average, 2 standard deviations, and this one's below average, 3 standard deviations. So we know that 88% of our students, at least 88.9% of our students, scored between a 44 and a 134. So between 44 and 134 is what 88.9% of our students scored on that science test. Let's do the same thing for English. So for our English test, we're going to do the exact same thing. We're going out 3 standard deviations to get to that 88.9%. So again, I start with my mean here in the middle, but this time, instead of adding 15 each time, I'm going to add 10 each time because my standard deviation is 10. The average distance a data point is from the mean is 10. So I'm just going to add 10, add 10, add 10, subtract 10, subtract 10, subtract 10. So I know at least 88.9% of the students scored between a 42 and a 102. I know that at least 75% of the students scored between a 52 and a 92. So to answer this question, it's between a 42 and a 102 is where at least 88.9% of the students scored. So you can see that with the mean and the standard deviation, we can figure out where most of our data lies. Let's learn about the z-score. The z-score, or sometimes called the standard score, just tells us how far away or how many standard deviations a data point is from the mean. So that's all it does, is tell us how far away from the mean a specific data point is. Let me give you an example. So suppose that in one small town, the mean household income is $34,200 with a standard deviation of 2,200. We're going to find the z-score for 36,400 and for 29,800. So remember, this z-score just tells us how many standard deviations this number is from the mean. I'm going to draw a number line to help me determine this. So first, I'm just going to look at this number line, and right in the middle, I'm going to put my mean. So my mean here is 34,200. That is my mean. Then I'm going to add my standard deviation, 1 without. So the average distance that a data point is from the mean is 2,200. If I add that, I get 36,400. I'm going to do that again. I'm going to add it again, and I get 38,600. Then I'm going to go backwards standard deviation. So this is 1 standard deviation above the mean. Or we say that the z-score there is equal to 1 because this value is 1 standard deviation above the mean. 38,600 is 2 standard deviations above the mean. So we say that the z-score there is 2. I'm going to go backwards. So I'm going to subtract 2,200, and I end up with 32,000. That number is 1 standard deviation below the mean. So therefore, the z-score, or the standard score for that particular data value, would be z equals a -1. It's 1 standard deviation below the mean. If I subtract another 2,200, I'm at 29,800. That number is 2 standard deviations below the mean. So its z-score is -2. So that z-score just tells me how many standard deviations a number is above or below the mean. Notice that my positive numbers mean that it is above average, whereas my negative numbers tell me that a data value is below average. Now, to answer this question, what is the z-score for 36,400? Well, let's look up here. 36,400 is exactly 1 standard deviation above the mean. So that particular data value is z-score is 1. So this one, the z-score is 1 because it's 1 standard deviation above the mean. Let's look for 29,800. That one's z-score is -2 because it is 2 standard deviations below the mean. Now, these just happen to turn out to be on an exact standard deviation, but not all the data values would. Some of the salaries might fall in here. Some of the salaries might fall in the middle, or they might be further out. So these happen to be actually on the 1 and 2 whole numbers standard deviations away, but that's not always true. So we have a formula to help us to figure out exactly what the standard score, what the z-score is. Well, how do we do that? Well, notice that what we're doing is we're finding out how far away this is from that. In this case, it was 2,200 away from there. And then I divide by the width of my standard deviation. So the z-score formula looks like this. If I have a population, a census of data, I'm just using it. The two formulas are going to be identical. It's just the notation we use. If I'm talking about a population, then I take my data value and I subtract my mean to find out how far away they are. Then I divide by my standard deviation, that width, how far is each part away. For a sample, it's exactly the same formula, it's just the notation is different because instead of using mu for population, I use x bar for that sample mean. Both of those still mean mean though. And I divide still by my standard deviation. It's just we use an S for standard deviation there. So let's use that z-score formula to find the z-score for a data value. For instance, let's find the z-score for 35,520. So I'm going to find the z-score for that. Now we can kind of look up on my number line and figure out about how much it should be. 3,520 is going to be somewhere in here. So I know that my z-score should be somewhere between, by the way, the mean z-score is 0. So my z-score for this number should be somewhere between 0 and 1. It's not a full standard deviation away from the mean. So I'm just going to use my formula to help me. I take my 35,520, my data value. I subtract my mean, in this case, 34,200. And then I divide by the width of each one of these, or the 2,200, my standard deviation. So on top there, when I do this subtraction, I get 1,320. And on bottom, I still have the 2,200. Simplify a little bit. So I can divide the top and the bottom by 10. I can divide the top and the bottom by 4. 4 goes into that top 3 times with 1 left over. 4 goes into 12 3 times. 4 goes into 25 times with 2 left over. 4 goes into 25 5 times. I notice that those are double digits, so therefore 11 goes into both of those. If I divide the top by 11, I get 3. Divide the bottom by 11, and I get 5. Now, when we talk about standard deviations and z-scores, we like to use decimals to show those. So I'm going to turn that into a decimal. And if I make it into tenths, well, if I multiply this by 2, I get tenths. Multiply that by 2, and I get 6. So 3/5 is equal to 6/10. So we said that the z-score would be between 0 and 1. And sure enough, the z-score is there between 0 and 1. It's 6/10 of a z-score, of a standard deviation away from the mean. And it's above average because it is positive. So that's what the z-score tells us, is it just tells us how many standard deviations a particular data value is away from the mean. Let's use the z-score formula to find missing values. Remember that a z-score just tells us how many standard deviations a data value is away from the mean. And we have this formula to help us find that z-score, where if it's a population, we use this notation, and if it's a sample, we use this notation. But both the formulas are actually the same thing. We just take our data value and subtract our mean. And then we divide by the standard deviation. So we find the distance from our data value to the mean, that deviation, and we divide by how wide our standard deviation is, that width of our standard deviation. So let's use that formula to find a few missing values. Let's start here. We're given the mean is 45, the standard deviation is 5, and we have our data value is 42. And we want to know how many standard deviations is that from the mean. So we're just going to use our formula to help us. So z is what I'm looking for, and that equals my data value, 42, minus my mean, and I divide that by my standard deviation. So 42 minus 45, well, notice that that 42 is below average. It's smaller than the mean. So my z-score is going to end up being a negative number. 42 minus 45 is a negative 3. We like our z-scores to be in with decimals, so I'm going to turn this into a decimal. Decimals are with tenths, hundredths, thousandths, so I want my denominator to be 10. If I multiply this by 2 to get to 10, I have to multiply the top by 2, and that's 6. So 3/5 is the same as 6/10. So the z-score for that particular data value is a negative 6/10. This tells me it's below average, and it's not even one full standard deviation below the mean. Let's find our data value. This time we know our mean, we know our standard deviation, and we know the z-score. We know that our data value is below average, one standard deviation and a little bit more away from the mean. So if you think about the data values, if it's below average, it's going to be below that 620. And then it's going to be down more than 15 because it's more than one of these standard deviations away from the mean. I just used my formula to help me figure it out. In place of z, I'm going to put in the negative 1.2. I don't know x, so I'm going to leave that as an x. My mean is 620. And I fill in my standard deviation with 15. Now I'm going to solve. And in order to solve this, the first thing I need to do is get rid of this fraction. So this side is dividing by 15. To get rid of that 15, I'm going to multiply both sides by 15. If I multiply this side by 15 and I multiply that side by 15, this 15 divided by that 15 becomes 1. Then on the right here, I'm left with x minus 620. And on the left, I'm just multiplying 15 times 1.2, or 1 2/10. So 15, let's do that off to the side, 15 times 1.2. Ignore the decimal for a minute and just multiply. So 2 times 5 is 10, carry your 1. 2 times 1 is 2, plus 1 makes 3. Move over a spot for that tens place. So 1 times 5 is 5, 1 times 1 is 1. Add together. Now I'm going to worry about the decimal, and that decimal is just over one spot. So I put my decimal here. So it's just 1/15 and then 2/10 of that. So it's 18 when I multiply it. And don't forget your negative. A positive times a negative makes that a negative. Now I need to know what x is. To get x by itself, I'm now going to add 620 to both sides. Notice when I add it here, it makes it 0, and it just leaves me with that x on the right side. If I do it on the right for my equation, I must also do it on the left. And really I'm subtracting because their signs are different. 620 minus 18 leaves me with 602. So my data value is 602. Let's see if that makes sense. It is below the 620 like we said it was going to be. It's less than that because it was below average. And it's more than 15 away from the 620. Now let's do this last one. Here we don't know our mean. That's the one that's missing. We know the standard deviation is 10. We know our data value is 143. And we know our z-score is 2 2/10. Let's just fill that into our equation. So here our z-score is 2 2/10. And that equals my data value, 143, minus my mean, I don't know that, so I'm going to leave it as mu, over my standard deviation of 10. Just as I did before, to find my mean, I'm going to multiply both sides by that denominator to help me get rid of my fraction. So I'm going to multiply both sides by 10 here to help me get rid of that denominator. So on the right, I'm going to have 22. And on the left, this becomes 1. So I'm left with 143 minus that mean. I want to get the mu by itself. So I'm going to subtract 143 from both sides. But when I subtract 143, notice that on the right here, this becomes 0, and it just leaves me with a negative mu, a negative mean. That minus sign goes with that mean. But here, the signs are different, so I'm really subtracting. 3 minus 2 is 1, 4 minus 2 is 2, 1 minus 0 is 1, and then I keep the sign of the larger number, so negative 121. Now, I'm going to divide both sides by a negative 1 to find out what that mean is. Or you could multiply both sides by a negative 1 so that my mean is equal to, my mu is equal to a positive 121. Let's see if that makes sense. If my data value was 143, that's above average. And my z-score is positive to show that it's above average. And it's at least 2 of these above average, so 2 more, at least 20 above this. And yes, that is at least 20 above that. So my mean there being 121 makes sense. So remember, z-score just tells us how many standard deviations a data value is away from the mean. Let's use the z-score to help us to compare things. The z-score just tells us how far away a data value is from the mean in the units of standard deviations. In other words, it says how many standard deviations a data value is from the mean. using that, we can then begin to compare things that normally we can't compare. For instance, we can compare apples to oranges. Let's do this example. The average apple has a diameter of 3.25 inches with a standard deviation of 0.5 inches. The average orange has a diameter of 4.5 inches and has a standard deviation of 1 inch. If I have an apple with a diameter of 4 inches and an orange with a diameter of 5.5 inches, which fruit is largest compared to others of its kind? We can use the z-score here to find out which one is largest compared to its kind. So let's take this apple first, and here's what we know with the apple. We know that the average, the mean of our apples is 3.25. We know that the standard deviation of our apples is 0.5. And we know that the apple that we have has a diameter of 4 inches. So our particular apple has a diameter of 4 inches. Notice that our apple is above average. We're going to find how many standard deviations our apple is above the mean. So we're going to use our z-score to help us find out how many standard deviations it is above the mean. Remember, with our z-score, we take its z-score is equal to the data value minus the mean divided by the standard deviation. So I'm just going to fill in my values here. So my z-score, well, my data value minus my mean divided by that standard deviation. So for an apple, 4 minus 3.25 is 0.75. I'm going to divide that by 0.5. In order to get rid of the decimals, I'm going to multiply the bottom by 10 and the top by 10. So I just have 7.5 divided by 5. So now 5 goes into 7 one time with 2 left over. 5 goes into 25 5 times. So this apple is 1.5 standard deviations above the mean. So if we look at all apples, we can see that this is above average, and it's above average by 1.5 standard deviations. Now I'm going to do the same thing with my orange. I'm going to find out how many standard deviations the orange is from the mean. So I need those same data values. I need the mean of my oranges. Well, the mean of my oranges is 4.5 inches. And the standard deviation of oranges is 1 inch. And my data value, the orange that I have, is 5.5 inches. Notice that this orange is also above average. Just like my apple was above average, my orange is above average. So let's look and see if we can find the z-score for my orange. Again, I'm using my z-score formula to find out how many standard deviations this average is above the mean. I take my data value, I subtract my mean, and I divide by my standard deviation. So 5.5 minus 4.5 is 1. 1 divided by 1 is just 1. So this is 1 standard deviation from the mean. This orange is closer to average. It's closer to an average orange than this apple is to an average apple. This one's bigger compared to the other apples. While this one is above average, it's not as above average as the apple is. So when I look at my apple and my orange, my apple is better compared to other apples than the orange is compared to other oranges. So here the apple wins. So we can use that z-score to help us to tell which one is further from the average. Sometimes though, we would like our stuff to be closer to the average. Maybe if I'm a manufacturer and I want something to be close to the average, then having a z-score that's close to the average, that's closer to 0, would be better. So it depends on the scenario when I'm comparing those things. Let's use the z-score to help Tim make a decision about taking a job. So Tim lives in Normalville, USA, where he has a salary of $42,000. The mean salary in Normalville is $42,800 with a standard deviation of 1,000. He's offered a job in Weirdville, USA, making $55,000. The mean salary in Weirdville is $57,200 with a standard deviation of 2,000. Which town would Tim do better in compared to others in the town? So Tim's trying to make a decision about which town to live in, and he decides to find the z-score to help him make that decision. Remember, the z-score just tells us how many standard deviations away from the mean a particular data value is. And we can use this formula to help us find the z-score, where our z-score is just the difference between our data value and the mean divided by the standard deviation. So let's look through and find those different values. In our problem, his salary of $42,000 is our data value. The mean is $42,800. And the standard deviation is 1,000. So we can already tell just by looking at these numbers that Tim makes below average salary. And we just want to know, how does he fare compared to the rest of his compatriots, the rest of the people in his town. So I'm just going to take and find out how many standard deviations he is away from that mean. Take my data value of 42,000 and I subtract my mean of 42,800 and I divide by my standard deviation. Remember that when we're subtracting and we have the smaller number before a bigger number, it's going to end up being negative, but we just subtract as always. This is just 42,800 minus that 42,000, which gives me 800. But since this number is bigger, it's negative. And we're dividing that by 1,000. I'm going to do a little bit of simplification. Notice that if I divide by 100 on top and bottom, I end up with a negative 8/10. Or I could write that as negative 8/10. So his z-score is below average. We knew that just by looking at the numbers. And he's not a full standard deviation below the others. The closer to 0 we are, the closer we are to average in a town or with a value. Let's look at Weirdville now. In Weirdville, he'll be making $55,000. That's more than what he's making there in Normalville. The mean in Weirdville is 57,200. And his standard deviation then is 2,000 in that town. So let's find compared to Weirdville, how will he be doing? So let's take our z-score there, take your data value, subtract the mean, and divide by the standard deviation. Again, he's below average, so we're going to end up with a negative z-score. I'm going to subtract this 55,000 minus this. So it's going to end up being negative, but it's still just subtraction as always. 200 there on the end. 57 minus 55 is 2. So I end up with 2,200 on top divided by 2,000 on bottom. We can divide the top and the bottom by 100 to simplify that fraction, and we end up with negative 22 over 20. I'm going to divide the top and the bottom by 2, so I end up with negative 11/10. So a negative 11/10 is negative 1.1. So he is below average, more than one standard deviation below average. This one is closer to average than that one. So he will fare better. He's better compared to his neighbors in Normalville than he is in Weirdville. In Weirdville, he'll be making less compared to the people around him. Maybe he should just stay in Normalville. That's how we can use the z-score to help us to make decisions. Math Made Simple at Simpson Math. Thanks for watching. Hello, I'm Patty Simpson with Simpson Math. We're going to create a box and whisker plot. A box and whisker plot just helps us to see how spread out our data is. Let's look at a 5-number summary. The 5-number summary are just the 5 numbers that we use in a data set that divides that data set into quartiles, or you can think of it as into fourths, so that we have 4 even parts in our data set. And the 5-number summary includes the minimum value of the data set and the maximum value of the data set. Then we're going to find the median of our data set, and so that we're splitting the data in half. 50% will be below the median and 50% will be above the median. Then we're going to take each one of those halves and cut them in half so that we end up with fourths. And this Q1 is going to be the median of that bottom half, and the Q3 is going to be the median of the top half. And that Q just stands for quartile. The upper bound of the first quartile, the upper bound of the second quartile, the upper bound of the third quartile, and then our maximum would be the upper bound of that last quartile. So let's go through and find our 5-number summary for this data set. The first thing we're going to find is the minimum value. And that minimum is just the smallest number. So in this case, 59. Then I'm going to find my maximum value. My maximum value is just the largest number in my data set, in this case 105. Then I'm going to find next my Q2, Q2, which is our median, so the one that is right up in the middle, so that half is below and half is above. So let's count to see how many data values we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Remember that to find the median, we can take that 15 and divide it by 2. So 15 divided by 2 gives me 7.5. And then round it up to the next one so that we're looking at the 8th data value is going to be our median. So 1, 2, 3, 4, 5, 6, 7, 8. This 75, 1, 2, 3, 4, 5, 6, 7 is above, and 1, 2, 3, 4, 5, 6, 7 is below. So we've split our data set in half. That 75 is our Q2. Then, to find our upper bound of our first quartile, we're just going to find the median of the bottom half. So I'm going to look at this bottom half of my data, and I'm going to find the median. So again, there were 7 down here, so divide that by 2, and that's 3.5. Round it up 1, or up to the nearest whole number, so you end up with 4. 1, 2, 3, 4. This 4th guy is going to be our Q1. Notice that there are 3 below him and 3 above him. So we now have 1, 2 pieces. We're going to do the same thing on the other end. Our Q1, though, is that 67. It's the median of the bottom half. Now, our Q3 is just the median of our top half. So ignore this bottom half and just look at this. And again, it should be that 4th one. 1, 2, 3, 4. So this 79 is now our Q3. 79 is our Q3. We've now divided our data into fourths. Here's 1, 2, 3, 4 parts there. So we've divided it into quartiles. That's what that 5-number summary does. Then also when we make a box and whisker plot, we're going to use these 5 numbers to help us make our box and whisker plot. Let's look at the interquartile range. The interquartile range is just the difference or the range from Q3 to Q1, from the upper bound of our third quartile to the upper bound of our first quartile. And that IQR is just a measure of dispersion, or how spread out our data is. Inside the IQR, there's 50% of our data. So if you think about on here, we've divided it into fourths with our 5-number summary. In this middle piece from Q1 to Q3 is half of our data. Half of our data sits here in the middle between those 2 numbers. So 50% of our data is in that interquartile range. So to find the interquartile range, all we do is take Q3 and subtract Q1. We found our 5-number summary here. Let's just take our Q3 and subtract our Q1. So Q3 was 79, Q1 is 67, and so the interquartile range here has a difference of 12 units. The range from one end to the other is 12 units long. And that tells us that the 50% of our data is within 12 units of itself. Remember when we talked about me owning a bar and how I asked all my patrons how much they made a year, and they said $35,000? But then in walked Ryan from YouTube and Ryan's Toy Review, and he made $22 million a year. And he really skewed my data. We would call Ryan an outlier. He's so far out there that he's messing with my data, and he's not a usual data value. He's outside the norm. He's not a normal data value. But what makes an outlier an outlier? How far would someone have to be out there in order to be considered an outlier? Like if Ryan made $50,000 a year, would that make him an outlier? What about $40,000 a year? What is it that makes him an outlier? So we're going to actually define what an outlier is, so that when we look at our data, we can say that one is too far out there. We're going to call it an outlier. And in order to define an outlier, we're going to say that it's anything larger than our Q3. So that upper third quartile, where a fourth of our data is here, we're going to take this Q3 and we're going to add on to it 1.5 IQRs. So we're going to look at our IQR and we're going to add that onto it, and then a half of that and add it on too. And if we go that far out, if it's more than the range of our middle 50% plus another half of that range, and add it on to this Q3. If it's that far out there, then we're going to say it's too big, it's an outlier. Or it could be on the too small of an end. Maybe one of my patrons didn't make any money at all. Would that make him an outlier? Well, in order for us to find out, what we'll do is take our Q1, that bottom or the top half of our first quartile, upper bound of our first quartile, and subtract from it 1.5 of these IQRs. So anything smaller than that or bigger than on the other end, we will call it officially an outlier. So let's see if we have any outliers in our data set. The first thing that we're going to do is find 1.5 of these. Well, 1/12 is just 12. What's half of 12? That's 6. So 12 plus 6 is 18. So 1.5 times the IQR, you can also do it this way. You can take 1.5 times the 12, which equals, well, half of 12 is 6. 6 times 3, so half of 12 is 6, and 3 times 6 is 18. So I'm going to take, that's 1.5 IQRs. We'd already figured that out. It's 12 plus half of 12 is 6, makes 18. We're going to take that 1.5 IQRs and we're going to add it to this Q3. And anything bigger than that, we're going to consider an outlier. And then we're going to subtract it from this Q1, and anything smaller than that, we're going to consider an outlier. So I'm going to back up a little bit so I have some room. Here's my 18. I'm going to take that 18 and I'm going to, let's first subtract it. We're going to take Q1 minus that 18. So 67 minus 18, well, down 10 and I'm at 57, down 8 and I'm at 49. So anything lower than 49 is an outlier. We don't have any smaller than 49, so we don't have any outliers on the smaller end. So then I'm going to take my Q3 and I'm going to add 18. So Q3 is 79, I'm going to add 18, which is 89 plus 8 makes 97. Anything bigger than 97 is an outlier. So in this case, do we have anything bigger than 97? Sure enough, this 105 is an outlier. That is an outlier. So we use this definition to help us to find our outliers. Now we're going to use everything we've just found and create a box and whisker plot or a box plot. A box and whisker plot is just a graphic way for us to display this 5-number summary. And this 5-number summary is going to help us to show the spread of our data, show how spread out the data is. So the way we make a box and whisker plot is first we're going to have a number line, and we need to make sure that that number line includes all of our data values. So I need to make sure that it goes from 59 to 105. So I need to pick some number to count by that is a consistent amount. So to make it from 59 to 105, I think I'm going to count by 2s to make sure I get there. And so I'm just going to start a little below that. I'm going to start at 58, just a nice round number to count by 2s. So 58, 60, 62, so the same distance each time, and I'm just counting by the same amount each time. 64, 66, 68, 70, 72, 74, 76, 78, 80, 82. What we cannot do is skip to like 100 now. We have to keep counting by 2s the whole way. So once you've picked that value to count by, continue to count by it until you get to the end. So 96, 98, 100, 102, 104, and 106. Next, what we're going to do is we're going to put a dot at our minimum value. So at 59, I'm going to put a dot there at 59. Then I'm going to go out to my maximum value, and I'm going to put a dot at that maximum value. So my maximum value is at 105. Then at 67, at Q1, Q2, and Q3, I'm going to draw a line at each one of those. So at 67, I'm going to draw a line. At 75, I'm going to draw a line. And at 79, I'm going to draw a line. I'm going to connect this interquartile region with a box. hence the name of box plot. Then I'm going to connect my box to its whiskers. So this line here is its whiskers. Therefore, it's a box and whisker plot. And it shows me how spread out my data is. 25% of my data is in this whisker because we divided this into quartiles. So 25% of my data is here, 25% of my data is there, 25% of my data is in here, and 25% of my data is there. Or inside the interquartile range, 50% of my data, 25 plus 25 is 50% of my data is inside this little box. So there's a box and whisker plot. But we found an outlier. That 105 is an outlier. And we actually don't include those outliers on our box and whisker plot because it makes it look like this last 25% is really spread out. When in reality, most of it is really close together. It's just that one guy that's way out there. So instead, what we do when we have an outlier is we don't include him as part of our whisker. Instead, I'm only going to stop at 81. I still call 105 my maximum number, but I'm going to stop my whisker now at 81. So that my whisker is right there. Look how much smaller that is. It shows me that that last quartile is actually not very spread out at all. Then that 105, I just put a little asterisk out there that says 105 is an outlier on my data values. If that 105 doesn't fit on my box plot, I can just put a little asterisk somewhere here to let me know that that's an outlier. Then, like all other good graphics, my box and whisker plot needs to have labels and a title. So down here, these numbers were the speed in miles per hour. So I just need to let my reader know that this was the speed in miles per hour. And then I need to have a title on my box and whisker plot. So in this case, it was the speed of motorists, or something to that effect. So there we have created a box and whisker plot of our data there of those speeds. And it just shows us how spread out our data is. So in this case, you can see that on this 25%, it's more spread out than it is on that 25%. If we didn't have that 105 there, this would be left skewed because these on the left would skew my data to the left. But that 105 over there really makes it skew to the right instead. So that's what a box and whisker plot does, is it shows us the spread of the data. Let's create a box and whisker plot from start to finish. I have some data here. The following speeds of motorists in miles per hour recorded one Monday. The box and whisker plot is going to show the dispersion or the spread of this data. To create that box and whisker plot, the first thing we need to do is find the 5-number summary. Remember that the 5-number summary is the minimum value, the maximum value, our Q2 is our median, and then the Q quartile, the first quartile, is the upper range of that first quartile, or it's the median of the bottom half. And then Q3 is the upper range of that, or upper bound of that third quartile, and that is the median of the top half. So let's find these values. The minimum value is 46. The maximum is 81. Our median is that number that's straight in the middle of our data set that splits the data in half. So let's count how many numbers we have in our data set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We can take that 14 and divide it by 2. 14 divided by 2 is 7. So I know that because this is an even data set, I'm actually going to have two numbers in the middle. It's going to be the 7th and the 8th number. 1, 2, 3, 4, 5, 6, 7, and 8 number. So I'm looking in the middle of that 70 and 71. Right smack dab in the middle of that is going to be my Q2. Well, the number that's in the middle of that is 70 and a half, 70.5. You can find that by adding the two numbers together and dividing by 2 if you need to. Remember, that's just the midpoint. So in between those two is 70 and a half. Notice that when I do that, that 70 and a half splits it in half so that there's 7 data values on the left and 7 data values on the right. Then the Q1 is the median of this bottom half. So I'm going to find the middle number of this bottom half. Well, I know I have 7 values, data values on the left. Half of 7 is 3.5. Because it's odd, I'm just going to have one number in the middle. So I'm going to round it up to the 4th one. 1, 2, 3, 4. This one should be my Q1. I can check it. There are 3 here, there are 3 there. So the same number of numbers on each side. So 65 is that Q1, the median of the bottom half. Now I'm going to find the median of the top half the same way. There are 7 data values in here. 7 divided by 2 is 3.5. Because 7 is odd, I'm just looking for one number. 1, 2, 3, the 4th number. Again, notice I have 3 and 3 there. So my Q3 then is 78. I've divided my data set into fourths, into quartiles. Here's the first quartile, the second quartile, the third quartile, and the fourth quartile. And I've created my 5-number summary. We need that to make our box and whisker plot to show how spread out our data is. The next thing we need to do is find the interquartile range. So our interquartile range, remember, is this range from Q3 to Q1. How far is that range? So I'm going to take, to find my interquartile range, I'm going to take my Q3 minus my Q1. So 78 minus 63 is 13. So the interquartile range is 13. Now I'm going to check for any outliers. Is there anybody out there who was going too fast, so fast that we're not going to include him on our box plot? Or is anybody that was going too slow, so slow that we're not going to include them on the box plot? So I need to find those outliers to know if everybody gets included in this box plot or not. To find the outliers, I look for 1.5 IQRs. So I need 1.5 of these. Well, one of those is 13, and then half of that is 6.5. So I'm going to add that together. Or you can just multiply by 3 halves. 1.5 times the 13 will multiply straight across with fractions. You just multiply straight across. So you end up with 39 on top, 13 times 3 on top, and on bottom it's 2. Divide that, 2 goes into 3 one time with 1 left over. 2 goes into 19 9 times with 1 left over. 2 goes into 10 5 times. So 19.5 is 1.5 of these IQRs. Now to find the outliers, we're going to take that 19.5 and we're going to add it to the end of this Q3. So I'm going to take my Q3 and add that 19.5, and anything bigger than that is going to be considered an outlier. So my Q3 is 78 plus 19.5 is, well, we have 0.5, 9 and 8 is 17, carrier 1, 8, 97.5. So anybody that's going faster greater than 97.5 is an outlier. We don't have anyone traveling faster than 97.5, so we don't have an outlier on that upper end. Let's see if we have an outlier on the lower end. See if this 46 is too slow, if we consider him an outlier. So we take this time our Q1, that bottom quartile, and subtract off the 19.5, 1.5 of those IQRs. So my Q1 is 65, and I'm subtracting almost 20, so it's going to take me down to almost 45, but not quite. So 45.5. So anyone who's traveling less than 45.5 is going to be an outlier. Oh, so that 46 is not an outlier. It's barely not an outlier, but by our definition, that's not too slow. So we don't have any outliers for this particular box plot. Now, I'm going to make my box and whisker plot. I'm going to use all this information to create it. And to create it, we draw a number line. And we have to decide what we're going to count by. I need to count so that my numbers go from 46 all the way to 81. So that's a, not quite 40 distance there. So maybe if I count by maybe 5s, or I want to do it as small as I possibly can without making sure that I get it onto the number line. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I can count by 2s and get it all on there. So I'm going to use that. I'm going to count by 2s. I'm going to start with 46 and count by 2s all the way across. Once you've decided on what you're counting by, you must keep that consistent measure all the way through. And you really do want to be able to count as small as possible so that you're not distorting your data. You want to count as small as you possibly can to make sure that you get it all on there. So, if I couldn't have fit all with 2, maybe I would have tried 3. And then 4 to see. Now, I have my number line done. I'm going to just put the 5-number summary on my number line. So at my minimum, I put a dot. And at my maximum, I put a dot. At my Q1, I put a line. So at 65, I put a line. At 70.5, I put a line. And then at 78, we draw a line. To show that interquartile area, this 50% of my data, I'm going to draw a box, hence the name box plot or box and whiskers. Then so 50% of my data is in here, 25% there and 25% there. I'm now going to draw this line down to my bottom mileage. So 25% of my data is spread out along this. And then I'm going to draw one more last line from my box to my maximum. And 25% of my data is spread out here in this whisker. So you can really look at the spread and see that the bottom fourth of your data is really spread out, whereas the top fourth of your data is really close together. And it just shows us what that range is in the middle as well. So we really get a good idea of dispersion with the box and whisker plot, or how spread out our data is. Now, with all good displays, we need to have labels. So what are these numbers down here? These are speeds in miles per hour. And then I need a title for my box plot to let my reader know if they want to actually look and see what the information is. So all good displays have those titles. So when we're creating box and whisker plot, there's several steps we have to go through. First, we have to find that 5-number summary. Then we need to find the interquartile range, this distance here. And we use that distance to find the outliers. We're going to take one of those and another half of that and add it on. And anything bigger than that is an outlier. And then we do the same thing backwards. We take one of those and half of that, and we add it on to the end here to see if this is an outlier. That barely wasn't. So then once we found our outliers, we can create our box and whisker plot using our number line. And that's a great show, a great display for dispersion. Math Made Simple at Simpson Math. Thanks for watching.